Okay, so today we continue our discussion of basic principles of functional analysis. There are three basic principles, and we have already proved two of them. Namely, we have proved the Hahn-Banach theorem and the Banach-Steinhaus theorem. And today we are going to prove the third basic principle, namely the open mapping theorem. So this is a fundamental result due to Stefan Banach. And we will see that this result has several equivalent forms. So theorem 1. Theorem 1, this is the open mapping theorem. Suppose that X and Y are Banach spaces, and T is a surjective bounded linear operator of X onto Y. Then T is open. T is open. So let's recall that in general, an open operator between normal spaces is always surjective. So this theorem states that if the spaces are Banach spaces, then the converse is also true. A surjective operator is open. The proof will be divided into two steps. The first step will require the completeness of Y, and the second step will require the completeness of X. So to begin with, let's introduce the following definition. Suppose that X and Y are normed spaces, and T is a linear operator from X to Y. So at this point, I don't assume that T is bounded, just a linear operator. We say that T is almost open if there exists a positive number R such that the closure of the image of the open unit ball of X contains the ball of radius R. Contains the open ball of radius R. Let's compare this definition with the definition of an open operator. So remember probably that a linear operator is open if and only if the image of the open unit ball contains a ball of positive radius. So the difference is that here we take the closure. And it's clear that, let's observe that each open operator is almost open. In general, the converse is not true. There are very simple counterexamples. For instance, you can take an incomplete normed space and consider the embedding into its completion. So this map is obviously almost open, but it is not open because it is not surjective. Now we have the following lemma. This is lemma 1. Lemma 1. Suppose that X is a normed space and Y is a Banach space. And T is a surjective linear operator. Surjective linear operator from X onto Y. Then T is almost open. T is almost open. The proof takes less than a line. It's enough to observe that if we take the closure of the open unit ball, then the set is a barrel. This is a barrel in Y. So let's recall that a subset of a normed space is a barrel if it is absolutely convex, closed, and absorbing. So this set obviously has all these properties because the image, well, the open unit ball is of course absolutely convex, and the image of an absolutely convex, the linear image of an absolutely convex set is absolutely convex. Also, it's very easy to show that the closure of an absolutely convex set is also absolutely convex. And finally, this set is absorbing because T is surjective. So this set is a barrel, and in the previous lecture we proved that a barrel in a Banach space, and Y is a Banach space, contains a neighborhood of 0. And this is exactly what we wanted to show. So this completes the proof. Okay, now lemma 2. Now we suppose that X is a Banach space, Y is a normed space, and T is a bounded linear operator from X to Y. And let's suppose that for some positive R, we have this inclusion. I claim that we actually have a similar inclusion without taking closure here. This looks a little bit unexpected because this seems to be weaker than this inclusion, but they are actually equivalent. So in particular, we see that if T is almost open, then it is open. So an almost open operator from a Banach space to a normed space is open. So for simplicity, we can assume from the very beginning that R equals 1. Because if not, we can just rescale the norm on Y. So we multiply the norm of Y by a suitable constant, and this reduces everything. So this reduces everything to a case where R equals 1. Then by linearity of T, we have the following inclusion. So this inclusion holds for each positive row. It holds when row equals 1, and by linearity it holds for each positive row. So we want to show that the image of the open unit ball contains the open unit ball. So we take an element Y in the open unit ball of the space Y. And we choose a positive row such that row is positive, such that the norm of Y is less than the row. A row is less than 1. So since the norm of Y is strictly smaller than 1, we can always find such a number rho. Now let epsilon be 1 minus rho. So this is a positive number. And so we see that Y now is in the open ball of radius rho. So by using this inclusion, we see that there exists an element in x1 in the open ball of radius rho such that y is approximated by the image of x1, such that y minus tx1 is very small. Well, it will be convenient to choose x1 such that this number is less than epsilon over 2. Okay, now let's apply the same argument to this vector. So it sits in the open ball of radius epsilon over 2. So again, by the same inclusion, we see that there exists a vector x2 in the open ball of radius epsilon over 2 such that the image of x2 approximates this vector. In other words, we can always find x2 such that the following inequality holds. And then we repeat this procedure. Now we take this vector, it sits in the open ball of radius epsilon over 4, and we can approximate this vector by the image of a certain vector x3, which sits in the open ball of the same radius. And we continue this procedure. So at the nth step, we find a vector xn, which sits in the open ball of radius epsilon over 2 to the power n minus 1, such that we have the following inequality. So the image of this vector approximates y minus the sum from 1 to n minus 1. Okay, so let's now look at this construction. First of all, we observe that if we take the following, if we look at the following series from 1 to infinity, then the first member is less than rho, strictly less than rho. The second one is strictly less than epsilon over 2. Next we have epsilon over 4, and so on. So what is this? The sum of these members is epsilon. So this is rho plus epsilon. Rho plus epsilon is 1. So this is 1. In particular, we see that this series is absolutely convergent, but X is a Banach space. X is a Banach space, and each absolutely convergent series in X converges. So we see that there is an element X, which is the sum of the following series. And moreover, the triangle inequality and this estimate implies that X, the norm of X, is strictly less than 1, because here we have the strict inequality. Okay, and finally let's look here. So let's denote this inequality by star. If we now let n go to infinity here, we see that T of x equals y. If we let n go to infinity, then we see that y equals T of x. And since x is in the open unit ball, we see that y sits in the image of the open unit ball. That's it. So y was an arbitrary vector in the open union ball of y. So we conclude that the following inclusion holds. And this is exactly what we wanted to show. So this completes the proof of lemma 2. Okay, now to prove the open mapping theorem, we simply combine lemma 1 and lemma 2. So if T is a surjective operator from X to Y, then since Y is a Banach space, lemma 1 implies that T is almost open, but X is also a Banach space. Now we apply lemma 2, and we conclude that T is open. Okay. Let's now look at some corollaries, which are actually equivalent forms of the open mapping theorem. Theorem 2, this is the so-called inverse mapping theorem. If X and Y are Banach spaces, and T is a bijective bounded linear operator from X to Y, then T is a topological isomorphism. Well, so clearly this is a special case of the open mapping theorem, because T is open, and the bijective open map is nothing but a topological isomorphism. But actually, it's quite easy to show that this result is equivalent to the open mapping theorem. This is one of the exercises in the exercise sheet 4. Another equivalent statement, theorem 3. Again, suppose that X and Y are Banach spaces. And suppose that T is a bounded linear operator from X to Y. Then T is topologically injective if and only if its image is closed in Y. Oh, sorry, the image of closed, and of course, and T is injective. In other words, topologically injective operators are the same as injective operators with closed images. Well, first of all, let's observe that the left to right implication is more or less obvious. And in fact, we have already used this implication at least twice. Well, indeed, if T is topologically injective, then the image of T is topologically isomorphic to X. Now X is complete, so the image of T is also complete. And a complete metric space is closed in any bigger space. This implies that the image of T is closed in Y. And by the way, here we didn't use the assumption that Y is a Banach space. Only the completeness of X is essential here. And the right to left implication follows from theorem 2, Well, indeed, we simply apply theorem 2 to the same operator T, considered as an operator from X onto the image of T. So since T is injective from X to Y, then T is bijective between X and the image of T. The image of T is closed in Y, and Y is complete. So the image of T is also a Banach space. And by theorem 2, this operator is a topological isomorphism, or equivalent to T is topologically injective. Okay. And another equivalent form of the same theorem is the so-called closed graph theorem. Before we prove it, let's make some simple observations. So suppose that X and Y are normal spaces. Normal spaces. Let's define a norm on their direct sum. Define a norm on their direct sum by the following formula. The norm of a pair, x, y, which is an element in the direct sum, is the maximum of the norm of x and the norm of y. So we denote this norm like this. So the resulting norm in space will be denoted by the following symbol. So this is the direct sum equipped with the above norm. And we call this space the L infinity sum of x and y. Instead of taking the maximum, we could equally well take the sum of these two norms, and this would give us the L1 sum of x and y. But at this point, these objects are essentially equivalent for us. Here's a simple exercise about this space. First of all, the norm given by this formula determines the product topology. This norm determines the usual product topology on the direct sum. Second, it's also easy to see that x and y, the summons, of course we can consider them as vector subspaces in the direct sum. So they are closed. They are closed in the L infinity sum. And exercise 3, also very easy. The L infinity sum is a Banach space, even only if the summons are Banach spaces. Even only if x and y are Banach spaces. Okay, let's now suppose that we have a linear operator from x to y. Let T be a linear operator. Not necessarily bounded, just a linear operator. Let's consider the graph of this operator. We know the graph by gamma T. So this is the set of all pairs of the form Tx and Tx, where x runs over big X. So this is a subset in the direct sum, and we call it the graph. This is the graph of T. Let's observe the following. First of all, we observe that the graph gamma T is the kernel of the following operator. Let's denote this operator by S. It acts from the L infinity sum of x and y to y. And this operator is given by the following formula. It takes each pair xy to y minus t of x. So clearly the kernel of this operator is nothing but the graph of T. And since the kernel of a linear operator is a vector subspace, we conclude that the graph is a vector subspace in the direct sum. The vector subspace of the direct sum. So this is observation 1. And observation 2, if the operator T is bounded, then it's immediate that S is also bounded. Because the norm of this vector can be estimated as, say, 1 plus the norm of T multiplied by the maximum of the norm of x and the norm of y. That is multiplied by the L infinity norm of this pair. So S is also bounded, and the kernel of a bounded operator is closed. And we conclude that in this case, the graph of T is closed in the L infinity sum. So the graph of a bounded operator is closed in the direct sum. Our next result, the closed graph theorem, states that if x and y are Banach spaces, then the converse is also true. Therefore, it's the closed graph theorem. If x and y are Banach spaces, and if T is a linear operator from x to y, such that the graph of T is closed. So we suppose that the graph is closed in the direct sum. Then T is bounded. Well, the kernel, first of all, we know that an operator is bounded if and only if it is continuous. And the kernel is the preimage of 0. 0 is a point. A point is closed. The preimage of a closed set is always closed. So the kernel of any bounded operator is closed. And this implies that the graph is closed. The graph of T is closed. Okay, so now let's prove the closed graph theorem. Let's consider the following picture. So first of all, since x and y are Banach spaces, and since the graph is closed, we conclude that the graph is a Banach space, because it is a closed subspace in the direct sum, and the direct sum is a Banach space. And let's now look at the following picture. This is the graph. This is x, and this is y. here we have our operator t, and here we have the projections onto the first summoned and onto the second summoned. So p1 of xy equals x, and p2 of xy equals y. And clearly p1 and p2 are bounded. Let's now observe that P1 is actually a bijection. P1 is a bijection of the graph onto X. So, well, indeed, the inverse map is explicitly given by this formula. So now we apply the inverse mapping theorem. We apply theorem 2 to P1. Theorem 2 implies that P1 is a topological isomorphism. So this means that the inverse map, P1 inverse, is bounded. And since the diagram is obviously commutative, we conclude that T, which is P2 composed with P1 inverse, is bounded. And this completes the proof. To feel why this result is useful, I recommend you to do the following exercise, which is actually very easy. This exercise gives an equivalent condition. It gives a condition which is equivalent to the closedness of the graph. So suppose that x and y are normed spaces, and t is a linear operator from x to y. Then the graph of t is closed in the direct sum if and only if the following condition holds. For each sequence xn in x such that xn goes to 0, and such that t of xn goes to some element y, we have y equals 0. So if xn goes to 0 and txn converges, then the limit of txn equals 0. So this condition is equivalent to the statement that the graph is closed. This is a simple exercise. And let's denote this property by star. So now we have the following equivalent form of the closed graph theorem. Let it be theorem 4 prime. Suppose that x and y are Banach spaces, and t is a linear operator from x to y, satisfying this condition star. A linear operator satisfying condition star. Then t is continuous. And t is continuous, or equivalently bounded. But here I stress that it is continuous. So why is it useful? Well, let's look at this condition once again. So, and suppose that we want to prove the continuity of some operator simply by definition. We know that an operator is continuous if and only if it is continuous at 0. So if we want to prove the continuity of t by definition, by using the definition, we must prove the following. If xn goes to 0, then t of xn goes to 0. Condition star simplifies our job. So when proving then txn goes to 0, we may assume from the very beginning then txn converges. The sequence has a limit. This simplifies the proof of continuity in many concrete situations. And actually, there is a useful exercise in the exercise sheet 4, which shows, which illustrates how one can use this condition.
But there is sequences that has no limit, like txn. So if we can assume that it has limit, we can make a contradiction.
Well, if we know that t is bounded, then of course, if xn goes to 0, then txn must go to 0.
Yes, yes. If x is just, if t is just a linear map, we
Yeah.
can sometimes choose like xn, that xn goes to 0 and txn has no limit.
Of course, if t is unbounded. If t,
Yes. And
but if you want to prove that t is bounded or equivalent to continuous, then the point is that if we want to prove the continuity, we can check this condition. That's the point, which is easier than to prove the continuity by definition. Of course, there are unbounded operators for which this condition fails.
okay.
There are unbounded operators, and this condition fails for unbounded operators. But if we want to show that some operator is continuous or equivalent to bounded, we have to check this condition. And this is easier than to check the continuity by a definition. So that's the point. Okay. Our next goal is to discuss a subject which is usually called elementary spectral theory. I use the word elementary here in order to distinguish between this kind of spectral theory and more advanced topics in spectral theory, which will be discussed in the next course of operator theory in the next term. So the central notion in this theory is the notion of the spectrum of an operator. The spectrum of a linear operator is actually one of the most important invariants of the operator. The spectrum was introduced by Hilbert at the beginning of the 20th century when he started some problems in the theory of integral equations. Essentially, the notion of the spectrum is purely algebraic. So it can be defined for any element of any associative algebra. So to begin with, we discuss spectra. So spectrum of an algebra element. Well, maybe should we switch on the light? Because it's, well, is it better now? Is it okay for the recording? Okay, so first of all, we adopt the following convention. So from now on, our base field will be the field of complex numbers. And this is essential. So we will see soon that some of our results will be essentially based on this assumption. First of all, let's introduce some terminology. By an algebra, I always mean an associative algebra over the field of complex numbers. So what is this? This is an associative ring A equipped with a vector space structure over C together with a complex vector space structure such that these two structures, the ring structure and the vector space structure, are compatible in the sense that the multiplication in A is bilinear. The multiplication is bilinear over the complex numbers. And here, this property is equivalent to the following identity. If we have two elements A and B in our algebra, and the complex number lambda, then we have the following identity. So this property, together with the distributivity of the multiplication, gives us the bilinearity of this map. An algebra which has an identity element is called a unital algebra. So we say that A is unital if there exists an element denoted like this, or simply by 1, such that we have the following identity. So this is the identity element. I must say that in functional analysis, it is normal to consider algebras which are not necessarily unital. For the simple reason that many concrete examples of algebras which appear in analysis are not unital, and also many natural constructions over algebras always produce non-unital algebras. But for our purposes, this is not essential. So almost all algebras we are interested in this course are unital. One more definition. If we have two algebras A and B, then a map phi from A to B is an algebra homomorphism. If it is a ring homomorphism and a linear operator at the same time. If phi is a ring homomorphism and is linear over the complex numbers. And we say that phi is a unital homomorphism if it takes the identity of A to the identity of B. So if A and B are unital, then we say that phi is unital if it takes the identity of A to the identity of B. One more standard definition. If A is a unital algebra, then we say that an element of this algebra is invertible if there exists another element denoted by A inverse, such that the product of these two elements taken in any order equals 1. And I suppose you know from your algebra course that if such an element exists, then it is unique. And it is called the inverse of A. The set of all invertible elements in A will be denoted by A cross. So this is the set of all invertible elements of A. So clearly this is a group under multiplication, and it is called the multiplicative group of A. Okay, so now we are ready to define the spectrum. So here's our main definition. Suppose that A is a unit of algebra, and little a is an element of this algebra. We define the spectrum of A. So this is a set denoted in this way, or simply by sigma of A. And this is a subset of the complex plane, which consists of those numbers lambda for which A minus lambda 1 is not invertible. So the set is called the spectrum of A. Well, let's look at some examples. Example 1. Probably the simplest case is the case where A is just the field of complex numbers. In this case, it's clear that the spectrum of any element, lambda, consists only of lambda. Because lambda minus lambda is 0, this is not invertible. And if mu is not equal to lambda, then lambda minus mu is not 0, so it is invertible, because this is a field. Example 2. This is something more interesting. Suppose that X is a finite dimensional vector space. This assumption of finite dimension is essential. And so let A be the algebra of all linear operators on X. The algebra of all linear operators on X. Let's denote it simply by L of X. The algebra of linear operators. So we know from our linear algebra course that a linear operator on a finite dimensional space is invertible if and only if its kernel is trivial. This is a standard result from finite dimensional linear algebra. Hence, we see that complex number lambda is in the spectrum of T if and only if the kernel of T minus lambda is non-trivial. In other words, this means that lambda is an eigenvalue of T. So we conclude that the spectrum of T the spectrum of a linear operator on a finite dimensional vector space consists exactly of all the eigenvalues of T. In Russian, собственные значения. But of course, the assumption that X is finite dimensional is essential here. In general, if an operator is invertible, then of course the kernel is trivial. But the converse, in general, the converse is not true. So as a result, for any linear operator on any vector space, the eigenvalues are in the spectrum. But in general, the spectrum can be much bigger than the set of all eigenvalues. Example 3. Now suppose that X is any set, and let A be the algebra of all complex valued functions on X. The multiplication is pointwise. So clearly an element F in this algebra is invertible, even only if F is non-vanishing. And the inverse element is 1 over F. So we conclude that lambda is in the spectrum of F, if and only if the function F minus lambda vanishes somewhere. There is an element little x such that F minus lambda vanishes at x. That is lambda equals f of x. And we conclude that the image, we conclude that the spectrum of F, is nothing but the set theoretic image f of x. Moreover, essentially the same argument, or better, exactly the same argument, works for many other function algebras. For example, the same holds for the algebra of continuous functions on a topological space. Simply because if f is non-vanishing and continuous, then 1 over f is also continuous. So the same argument shows that the spectrum of an element of the algebra of continuous functions is given by the same formula. The same holds for the algebra of, for example, of smooth functions on any smooth manifold. And actually for many other algebras of functions. Okay, now example 4 is slightly different. Again, we suppose that X is a set, and let now A be the algebra little l infinity of X. So this is the algebra of all bounded functions on X. Well, let's take an element in this algebra that is a bounded function f. Why is it invertible? Well, it is invertible if and only if f is non-vanishing. This is a necessary condition. But this is not the end of the story, because 1 over f should also be bounded. Otherwise, if it is unbounded, then f will not be invertible in our algebra. So equivalently, this can be written as follows. this means that f is bounded away from 0. So this means that there is a positive epsilon such that the modulus of f of x is greater than or equal to epsilon for each x. In other words, this means that 0 is not in the closure of f of x. So this is the invertibility criterion in our algebra. And now we see that a complex number lambda is in the spectrum of f, even only if this condition fails for f minus lambda, if only if 0 belongs to the closure of f minus lambda of x. Or equivalently, if and only if lambda belongs to the closure of f of x. So we conclude that the spectrum of a bounded function, considered as an element of the algebra of all bounded functions, is the closure of f of x. So we see that the spectrum, in general, the spectrum depends on the algebra. If we take the algebra of all functions, then the spectrum is just f of x, and here the spectrum is the closure of f of x. One more example is the algebra Beagle infinity of essentially bounded measurable functions. So first of all, let's give the following definition. Suppose that x and mu is a measure space, and f is a measurable function on x. We say that a complex number lambda is an essential value of function f if for each neighborhood u of lambda, the measure of its preimage is positive. So in some sense, this means that f is somehow often appears close to lambda in the measure theoretic sense. So the measure of the preimage of each neighborhood of lambda is positive. By the way, I would like to stress that if lambda is an essential value, then lambda is not necessarily in the image of f. And the other way around. There are elements in f of x which are not essential values. Now we have the following example. This is our example 5. An example and exercise at the same time. So let A be the Beagle infinity algebra. So we know that this is a vector space of equivalence classes of essentially bounded measurable functions. And this is also an algebra with a pointwise product. So clearly the pointwise product of two essentially bounded functions is essentially bounded. The exercise is to show that the spectrum for the spectrum of each element of this algebra is the set of all essential values of f. Okay, so these are the basic examples. Let's now look at some simple algebraic properties of the spectrum. Well, first of all, we have the following proposition. Suppose that A and B are unital algebras. And phi is a unital homomorphism from A to B. Then, first of all, I claim that phi takes invertibles to invertibles. Second, for each element little a in A, the spectrum of its image, the spectrum of phi of A, is contained in the spectrum of little a. And finally, part 3, let's look at the following condition. Phi takes non-invertibles to non-invertibles. I don't claim that this condition holds for each unital homomorphism. This is not true. But this condition holds if and only if phi preserves the spectrum, if and only if this inclusion is an equality. For each element A, the spectrum of phi of A equals the spectrum of A. So phi takes non-invertibles to non-invertibles if and only if it preserves the spectrum. Excuse me? This is phi of A, this is A. Okay. Well, the proof is a simple algebraic exercise. Property 1 is almost clear. 2 easily follows from 1. And 3 is more or less the same. So if you look at the proof of 2, you will see that 3 is essentially equivalent. So these two properties are actually equivalent. So, well, anyway, this is a simple exercise. Let's now look at a special case. We have the following corollary. Suppose that A is a unital algebra. And suppose that B is a subalgebra of A, such that the identity of A belongs to B. So we assume that A and B have the same identity. Then, for each element little b in the smaller algebra, we have the following inclusion. So the algebra is bigger, the spectrum is smaller. That's the rule. Well, this is indeed a special case of the previous proposition, because we just consider the inclusion of B into A. The inclusion of B into A is a unital homomorphism, and so this corollary becomes a special case of this formula. Sometimes this inclusion is an equality, and there is a special name for this situation. So we give the following definition. We say that B is spectrally invariant. B is spectrally invariant in A if this inclusion is an equality. For each element little b, the spectrum of B calculated with respect to the bigger algebra equals the spectrum calculated with respect to the smaller algebra. And by using the third part of our previous proposition, we see that this is equivalent to the following property. Each element of B, which is invertible in A, is also invertible in B. So if we apply this inclusion to the embedding of B into A, we get an equivalent formula of this form. Each element of B, which is invertible in A, is already invertible in B. Here are some examples and counterexamples. First of all, we have already observed, actually we observe it here, that the algebra of continuous functions on a topological space is spectrally invariant in the algebra of all functions on the same space. For each topological space X. According to this means that if f is a continuous, nowhere vanishing function, then 1 over f is also continuous. Another example, if E is a Banach space, then the algebra of all bounded linear operators on E, B of E, is spectrally invariant in the algebra of all linear operators on E. Why is it so? This is just an equivalent form of the inverse mapping theorem. If you have a bounded operator, which is bijective, that is, which is invertible in this bigger algebra, then it is a topological isomorphism. In other words, the inverse mapping is also bounded. So this means that our operator is actually invertible in the smaller algebra. So the spectral invariance of this subalgebra is equivalent to the inverse mapping theorem. And on the other hand, we have already discussed a simple counterexample. If X is any infinite set, then the algebra literal infinity of X, of all bounded functions on X, is not spectrally invariant in the algebra of all functions on X. Well, indeed, we already know that the spectrum of function f, considered as element of this bigger algebra, is the set theoretic image f of x. And if f is bounded and we calculate the spectrum with respect to the smaller algebra, we get the closure of f of x. But of course, it's easy to show that if x is infinite, we can always find a bounded function whose image is not closed. And this will give us a counterexample. It shows that this algebra is not spectrally invariant. Okay, it's time to finish. There is another useful algebraic property of the spectrum, namely the spectral mapping theorem for polynomials. So this property will be discussed at the beginning of the next lecture. And after that, we leave pure algebra and we come back to functional analysis. So we began to study Banach algebras, which are quite important objects. And we will show that the spectrum of any element of a Banach algebra is compact and non-empty. This is a very important result in the elementary spectral theory. Okay, thank you.